Let's look at the concept of testing. Testing is a set of activities to detect faults to ensure that the behavior, performance, and stability of an application or system meets user requirements. The testing is implemented to meet the user's expectation level and requirements, verifies, validates that it works, and finds defects through it. Finally, based on the defect data, the risk information of the development project is quantitatively measured and reported to the decision maker. These test activities exist before and after the test. They include the series of activities such as test plan and control, selecting a test condition, designing a test case, checking the results of the test, evaluating the test completion and pass criteria, reporting on the test process and the system under test, testing closing or completion. The purposes of conducting testing in an enterprise are as follows. They are to find remaining defects, verify to meet specifications, ensure that users and businesses meet requirements, obtain confidence and information at the quality level, provide insights based on information to reduce the business risks, review development processes and raising issues, and verify the implementation of logical design and validate the system and software whether it is working properly. The cause of the software defect that occurs during the development is caused by the error of human being. It also happens due to time pressures, complex codes, complexity of the underlying environment, changes in technology or systems, and integration between numerous systems. Failure is caused not only by such defects, but also by environmental conditions. In other words, radiation, magnetism, electromagnetic fields, and physical contamination can also cause software defects. And these environmental conditions may affect the execution of software by changing hardware conditions. The following table shows the type of defect. Defects are largely divided into errors and failures. Errors collectively refer to all defects that occur during the development phases, and failure indicates an incorrect result that can occur during the production. The purposes and roles of testing according to the lifecycle aspect of software development are divided as follows. The development process is to create the situation with as many faults as possible to find and fix software defects. Here, the developer becomes the key player of this activity. Acceptance testing is the process of ensuring that the expected system is working and that it meets the requirements. Mainly customers and users will be the key players. Software quality assessment testing is the transfer the risk of releasing a system on a specific schedule to the development project stakeholders. Based on the defects discovered through testing, you can measure quality related to the functional or non-functional requirements and quality characteristics of the target software. Here, the key players can be a tester, quality assurance. Maintenance testing involves a regression testing process that checks for new defects injected when changes are made in the development process. The key player of maintenance testing can be developer, tester, or quality assurance. Operational testing is an assessment of the operational characteristics of a system, such as reliability or availability. The operator can be the key player. To perform effective testing, you first need to understand and apply the principles of testing. Let's take a look at the 7 principles of testing that are most often mentioned. First, testing is an activity that reveals that defects exist. Second, perfect testing is impossible. This is because there are a myriad of internal conditions in one program, combinations of all the values that an input can have, and also combinations of GUI event sequences. Third, testing should start early in development as much as possible. Fourth, defects are focused on specific modules. The modules can be defective as follows: modules that have a complex structure in themselves, modules with a large amount of interactions with other parts or modules of the system or software, modules that have a high degree of developmental difficulty or use the latest technology, modules that are newly developed without reusing the existing codes, bigger modules, or less experienced development teams may be defective. Fifth, it is the pesticide paradox phenomenon. That means if the insecticide is sprayed repeatedly, the insect is resistant and the insects no longer die. If you repeat the same test with the same test case, you will not find new defects anymore. If a test case designed using formal techniques is also repeated, the likelihood of continually discovering new defects is reduced. Sixth, testing is context dependent. There are situations that do not change in all tests. For example, they are key testing activities which are test project planning, application of standard techniques, independent testing environment, efficient and effective testing team organization, and formal reporting. Finally, seventh, it is the absence of errors fallacy. This principle means that if you cannot meet your user requirements or business requirements, it cannot be considered high quality even if you remove all the defects. Now let's discuss the testing process. As shown in figure, the role of the V model in testing is to provide an overview of how to approach the testing at each stage of development. Let's take a look at the basic concepts of testing through V models. Test levels mean components, that is unit testing, integration testing, system testing, and acceptance testing. Each test level is independent of each other and requires a different test plan and strategy. Also, because each level has dependencies on each other, you must have an exit and start criteria to move from one test level to another. Testing in the early stages of development refers to the static testing that finds defects while reviewing the output of the processes. Defect prevention testing can reduce testing costs that occur later in the development process through an early stage testing. Verification is the process of verifying that the deliverables at the development stage meet the conditions or requirements established earlier in the phase. Validation is the process of evaluating whether a requirement is satisfied in terms of a user perspective at the end of development. Validation is available in both static and dynamic testing. Testing at these various test levels is not just about running tests to discover defects. Testing should be coordinated and managed around a testing process that involves various components. Let's look at the testing process and its key activities. In the test analysis and design phase, they consist of reviewing the test basis, identifying the test situation, requirements, data, assigning the test techniques, evaluating the testability, and building the test environment. In the test implementation and execution stages, test case specification, prioritization, data generation, procedure creation, precedence testing, testing execution and result recording, and comparison with expected results are executed. In the assessment and reporting of completion criteria, confirmation of whether the completion criteria is made, and the development of final test report are executed. At the end of the test activities, work production inspection, testware keeping, and test process evaluation are performed. Test planning and controls are performed for every phase. Therefore, testing strategy development, risk analysis, team organization, and reporting are performed. Let's take a look at test design techniques for designing and specifying test cases. Test design techniques are divided into specification-based, structure-based, and experimental-based techniques. First, the specification-based technique is a black box test design technique. This is a technique for deriving a test case based on a requirement specification or a model specification without referring to the internal structure of the test items. They are the equivalence partitioning technique for designing the test case to perform as the representative values from equivalent classes for an input condition. The boundary value analysis techniques for designing the test case include boundary values because the possibility that the defect is found in the input values corresponding to the boundary of the equivalent partition, and a pairwise testing technique for designing and executing the test accordingly based on which a table is created, which each value required for testing is combined with other values at least once. In addition, a decision table testing technique in which a test case is designed to test a combination of an input value and a stimulus displayed in a decision table, a state transition technique for designing a relationship between events, actions, activities, states, and state transitions, and when the system is modeled as a use case, there is a use case testing technique that derives test cases from use cases. Next, the structure-based technique is a white box test design technique. This is a technique for deriving a test case by referring to the internal structure of the test item, that is, the source code, the control flow structure, the navigation structure, and the workflow diagram. This is a control flow testing technique that designs to test all possible event flow structures when they are executed through a component or a system, a basis path testing technique that expresses a program as a control flow graph and test basis paths existing on the graph, and an elementary comparison testing technique that derives test cases to test combinations of input values using the concepts of modified conditions and decisions. Finally, experimental-based techniques, as the name suggests, are techniques for extracting test cases from experience, intuition, and testers' technical abilities in similar applications or technologies previously handled by the tester. This includes exploratory testing, i.e., informal test design techniques that use the information gained while performing the tests to actively control the test design while the tester is performing the test and to design new and better tests, and a classification tree technique that designs the test cases represented by a tree to be performed in combination with the representative values of the input and output domains. This time, let's talk about testing level and technique. First, let's look at what testing level is. There are several levels of software testing. And, in principle, it is important to consider the subjects that performs the test, the purpose of testing, and the test environment at each level. The following can be defined independently depending on the test level. The general goal of the test level, the development artifacts that are used to derive the test cases, the test items, the typical defects and failures found, the need for test harnesses and tool support, a detailed testing approach, and testing owner or organization can be defined independently. As you can see on the V model, the test on the right side of the V model seems to be the test level. I will explain each test level. A unit test is intended to detect faults in a unit module. It is conducted by the development organization in the development environment. Integration testing is aimed at detecting faults at the interface between the unit modules. It is performed by a development or testing organization in a development or test environment. The system test is performed to validate the functional and non-functional test in an environment similar to the production environment. In particular, non-functional testing tests system performance and security. The executing entity will be a testing organization and conduct the testing in an environment similar to the actual user environment. The acceptance test verifies the consistency with the requirements, and the user performed this test in the user environment. This time, let's talk about the testing techniques. First, the white box testing is also known as structured or code-based testing. It is classified into static analysis that analyzes predefined errors by analyzing internal structure of implemented source code, and dynamic analysis, which detects errors that can occur in real situation through execution of program. As you can see in the picture, the series of activities in the box on the left is white box testing. There are two common white box testing techniques, structural techniques and loop test. Because the nature of the testing work is to analyze a vast amount of source codes, test activities is usually performed with the help of a support tool. White box testing typically has the following characteristics. It is performed when the black box does not know that all executable statements are executed. And it is executed when it is difficult to predict side effects by black box alone. White boxes can detect unnecessary functions in the software and typos in the software. The black box test and white box test have different types of defects to be found and must play a complementary role throughout the testing process. Secondly, it is the black box testing. It is also known as functional or specification-based testing, and it is a test which focuses on how the software works according to the requirement specification. It performs functional and non-functional testing based on requirement specification and external interfaces without reference to the internal structure of software modules or components or systems. Let's take a look at what we do in black box testing. Firstly, it analyzes the target with a requirement specification. Next, we will design a test case and update it periodically as the target changes, and perform the testing. Then, create and report the artifacts. Finally, you will perform the maintenance. As you can see in the picture, the series of activities in the box on the right is the black box testing activities. The techniques of black box testing include equivalence partitioning technique, boundary value analysis technique, cause and effect graph technique, and error prediction technique. For details, please see the screen. This time we'll look at daily builds and behavioral testing. Daily build and behavioral testing is a process that takes a series of tests that are required to recompile the software product on a daily basis and verify basic behavior. This process is a production phase and can be started when the project is somewhat stable and on track. This process can save a lot of time by reducing the likelihood of common and time-consuming risks, such as integration failure, poor quality, and low project visibility. This process provides the control function critical to projects in recovery state. For this process to be successful, the developer must adhere to this process and carefully design behavioral tests. A typical solution to this is build automation. There are some parts that can be automated to some extent, such as whether the function outputs the specified output according to the specified input and corrects the wrong value. It's called unit test to make this process convenient. There are a lot of unit test types. JUnit is the most popular on the Java side, NUnit on the C# side, and CPP-Unit and Unit Test++ on the C++ side are popular respectively. Seeing build automation and test automation as a single process and continuing them is called continuous integration. Daily build and behavioral tests can be used effectively for projects of any size and complexity. The effects of daily build and behavioral tests are as follows. You can minimize the risk of integration. One of the biggest risks faced by a project is that when you combine or integrate code that your team has worked on independently, the code does not suddenly work together after they are integrated. The later you find this incompatibility, the longer it takes to debug than which the integration process would start earlier. This is because the program interface is likely to change, and there is a chance that a major part of the system will be redesigned and implemented. In extreme cases, an integration error may cause the project to be canceled. As daily build and behavioral tests keep integration errors small and manageable, you can avoid uncontrolled integration errors. Daily build and behavioral tests can reduce risks such as low quality. Risks such as unacceptable or problematic integrations are associated with low quality risk. You can put quality problems under project control by running a minimum of behavioral testing on every code in the product every day. We want to put the system in a familiar and stable state and keep it up. This is simply not allowing the point where time-consuming quality problems can arise. And daily build and behavioral testing support defect analysis in the early days. As you build and test the product every day, it's much easier to figure out why a product is broken on a particular day. If the product runs on the 17th and is broken on the 18th, you can see what happened between the 17th and 18th that caused the product to break down. Let's say you want to build and test the product on a weekly basis. If so, the problem may have occurred at any point between 17th and 24th. Daily build and behavioral tests can support progress monitoring. If you build the system on a daily basis, the existing or non-existent features become clear. Both technical and non-technical managers can simply run the product and easily see how close it is to completion. Daily build and behavioral testing can also promote morale enhancement. As Fred Brooks pointed out, amazingly powerful morale can sprout when looking at a working product. It does not matter what the product is. Developers can just be excited to see how they draw rectangles. So every day, if you build a new one, you can keep the developer's morale to the top because the product runs a little bit more every day. Finally, daily build and behavioral testing can improve customer relationships. If your daily new build efforts have a positive impact on developer morale, it can also have a positive impact on customer morale. Customers may like to see improvements in progress, and new builds on a daily basis provide a clue to see the periodic progress. Let's continue to look at software development activities. Deployment activities consist of activities such as release, installation, and activation, deactivation, adaptation, updates, built-in, version tracking, uninstallation, and retirement. Firstly, the release activity includes all activities that prepare the system for integration and migration to the customer site during the end of development process. Therefore, the release activity determines the resources for operating on the customer site and determine the resources needed to gather information about the performance of follow-up activities in the deployment process. Next, it is the installation and activation activity. Activation is the activity that launches the running components of the software. For example, activation in a simple system involves establishing some form of command for execution. For complex systems, you need to have all the support systems ready for use. In a large software deployment, a working copy of the software can be installed on a production server in an operating environment. Other versions of the deployed software can be installed in the test environment, the development environment, and the disaster recovery environment. Deactivation is the opposite of activation, which means termination of execution for all components of the system. Deactivation is sometimes necessary to perform other deployment activities. Some software systems require deactivation to perform the updates. It is desirable to retire or dispose the infrequently used applications or old systems instead of deactivation. Adapt activity is a process for modifying a previously installed software system. Adapt is different from the update because the updates originate primarily from geographically separated software producers, whereas adapt is initiated by local events, such as changes in the customer site's environment. Update activity is a partial or complete substitution of a previous version of a newly released software system. Next, built-in refers to the mechanism for installation updates that are embedded in some software systems. The automation of these update processes can range from fully automated to user-initiated and controlled. For Norton Internet Security, this is a built-in system, a semi-automatic method of scanning and installing to update both the antivirus definitions and other components of the system. Other software products provide a query mechanism to determine when an update is available. The version tracking system enables users to find and install updates of software systems installed on their PCs and local networks. Uninstallation refers to the removal of a system that is no longer needed. This includes reconfiguration of other software systems affected by file deletion on the system. Finally, it is a retirement. Retirement refers to the cancellation of the software system marked as useless by the producer. This corresponds to the end of the software product lifecycle.